Hi, thank you for joining me for this video, which is a mathematical adventure. Really, it's experimental mathematics, and we are going to be looking at patterns with numbers that are found on a diagonal in a matrix. So experimental mathematics is really cool. It's something we can do these days because of powerful computers. And all we have to do is think of a question that we might be interested in. It could be a small thing, it could be a big thing, but if it strikes our fancy and gets our imagination going, then we can use computers to figure out the answer to that question and discover something, maybe. So that's experimental mathematics. So I was doing an exercise from an excellent textbook on getting proficient with using Mathematica, and the challenge was to make a matrix of consecutive numbers and then add up the numbers that are on the diagonal. So it only asked me to do this for one diagonal, but on a whim, this is how experimental mathematics starts out, usually just a whim, just a fleeting thought, like, maybe this would be interesting. I decided to figure out the code to do this for two diagonals and then look for a pattern amongst these diagonals. Maybe there's a pattern with two diagonals that I wasn't aware of. It's great when you don't know things, because then you could maybe find them out. So maybe an undiscovered pattern was hiding in plain sight, but it requires many tedious calculations to find, and that's the sort of task computers excel at. Trying to find it is, again, experimental mathematics, which is a lot of fun. I hope you'll see. So making the matrix. What is a matrix? A matrix is rows and columns, and so here are our rows, here are our columns. If we have several rows, we can stack them to get columns, and that new structure is called a matrix. Mathematica has a function to do just this called matrix form. If the rows and columns are the same size, like they are here, then it's a square matrix. And for a square matrix, the longest diagonal would start and finish in a corner of the matrix. So this is the longest diagonal, 1, 4, 9, 16. It starts at a corner and it finishes in a corner. And of course, another observation, which all follow from the fact that we're dealing with a square matrix, is that the longest diagonal is it has the same numbers as the rows or columns. So here I wrote that it's the same size. Technically, that's not right. It's not the same size, right, because of the Pythagorean theorem, but it has the same number of elements. So there are four numbers here, 1, 2, 3, 4, and there are four numbers here, 1, 2, 3, 4. 1, 2, 3, 4. So that's how we can make a matrix really fast in Mathematica. So now let's look at those diagonals. The longest diagonals. So the matrix, it's built from rows, and we will, in a sense, this is how the code will work. Grab a row, then grab one specific number from that row, and the number we grab happens to be part of the longest diagonal in the matrix. The process gets repeated for all the rows, thus building out the diagonal. So for the first row, we're going to grab 1. For the second row, we're going to grab 4, etc., etc. So there are two diagonals, and the code will be a little bit different because the diagonals are going in a different direction. But writing the code for one diagonal helps us write the code for the second diagonal because a similar thing is going on. So we're looking for a pattern, right? And patterns need lots of examples. So we're going to change the code a little bit. So instead of just getting one matrix and one diagonal, which is what we did here. This code made the matrix, this code grabbed this diagonal, this code grabbed the other diagonal. We're going to change the code so we could get lots of matrices and get lots of diagonals. And the nitty and gritty details of how the code was written will be the focus of a companion video that I'll do some other time. So right now we're just going to focus on the experiment and the results. So here are the results, and this is the exciting part. And we finished working on the code, and this code totals up the numbers in the diagonal, and then we take those numbers and we divide them by each other, and we plot it, and we get this graph that clearly shows a pattern. So it looks like the curve starts shooting up real fast, and then it slows down, and it only increases gradually. So gradually it looks like it may be approaching a limit, and the limit is 2. Like, will it ever reach 2? Doesn't look like it. So just to go over, we add up these numbers, 1, 4, 9, 16. We add up 4, 6, 6, and 4. We divide these two numbers together. We get a value, and we plot that value on a chart, and we do that for a bunch of matrices, and we get this. So now I did not know that before doing this. I did not know that there was this pattern that if you divide one diagonal by another diagonal in a square matrix, the limit will be 2. So now that we've done this for matrix of consecutive numbers, maybe we could try this for other numbers. Maybe a really famous set of numbers, like let's try this for the prime numbers. So we'll make matrices of prime numbers, of consecutive prime numbers, and look at their diagonals. So maybe we just discovered a new pattern in prime numbers. So this was 500 consecutive matrices of prime numbers, of consecutive primes, and we grabbed the diagonals, we added up the numbers in the diagonal, and we divided those numbers from one diagonal into another diagonal, and we plotted the values, and we got this. And this also looks like it is a curve with a pattern. There's definitely a pattern. So you could sort of tell by the way that there are prime numbers involved, because prime numbers, if you permit me to anthropomorphize them, primes like to defy you. If you try to place them in neat categories, they will jump around and they'll frolic and be just out of your grasp, even though they are right in front of you. Even if we zoom in on this part of the graph, they're going to be kind of like jumping around a little bit. So it's easy to go full poetic when discussing primes. So I'll save my prime poetry for another time. So anyways, back to the curve. So it looks like the curve starts shooting up real fast, and then it slows down, right? It only increases gradually, and it looks like it's approaching a limit. And in this case, the limit looks like it's 1. So those are our two findings. Here we're zooming, we hit a traffic jam, it's really crowded, and it looks like we'll never get past 2. That's consecutive numbers. This is consecutive prime numbers. We're zooming, it's getting really crowded, and it just slows down, and it looks like we'll never reach 1. So what does it mean? I don't know, but it's a really cool way to find a pattern. Just using experimental mathematics, just putting in some code and seeing what happens. I think this is a lot of fun, and there's definitely room for future research. We could try other famous sets of numbers. We could try to find a more generalized, formalized and generalized definition of what's going on. Thank you for joining me on this video. If you have any questions or suggestions, please comment below, and have a great day.